In this video, we're going to work through some exam solutions focused on the applications of derivatives. Question 1. Determine that a second derivative for each of the following functions. The first, we're going to apply the chain rule, and we can do that formally or informally. In this case, we're going to derive it informally. If we had let u equal 4 take 5x, the derivative is negative 5. So we're going to multiply by negative 5. Using the power rule, 4 comes to the front, and we subtract 1 from the power. So 4 times negative 5 is negative 20, times by the composite function 4 take 5x, all to the power of 3. The second derivative is applying the chain rule again. So negative 5 is the derivative of u. So negative 5 comes out, that's going to be multiplied there. We multiply the negative 20 by 3, subtract 1 from the power. So negative 20 multiplied by negative 5 is 100. 100 times 3 is 300. 300 lots of 4 take 5x to the power of 2. In the second case, I'm just going to expand. So 2x cubed times 3x is 6x to the 4. 2x cubed multiplied by 1 is 2x cubed. Makes it far easier to differentiate instead of using the product rule here. dy dx is 24x cubed plus 6x squared. And simply, now we can just work out the second derivative. The second derivative is 3 times 24 is 72. Subtract 1 from the power. 2 times 6 is 12. And we subtract 1 from the power, we're left with x. Question 2. Determine the coordinates of the point of inflection of the curve y equals 2x cubed take 12x squared plus 8x take 10. First of all, we're going to differentiate. This is a simple differentiation question where we're going to multiply 3 by 2 and subtract 1 off the power for each case. So first derivative is 6x squared take 24x plus 8. The second derivative is the same. 2 times 6 is 12, take 1 off the power. Negative 24x becomes negative 24, and the derivative of a constant is 0. For the point of inflection, we're going to let the second derivative equal 0. So the second derivative is 12x take 24. We're letting that equal 0. Now we can solve for x by adding 24 to both sides and dividing by 12. So the answer, or x, is 2. We're going to check for the change of sign. So either side of 2, we can see that we're getting positive results to the right and negative results to the left. That means the sign changes either side of that x equals 2 solution. The second derivative changes sign. So there is a point of inflection at x equals 2. We can then determine the coordinates of that point of inflection by subbing in 2 to the original function. So the coordinates of the point of inflection are 2, negative 26. Question 3. Consider the curve y equals negative 2x cubed plus 6x squared. This is another cubic. Describe the shape of the curve at x equals 3. Determine the first derivative by applying the power rule. So 3 times negative 2, 2 times 6, and minus 1 from each power. The second derivative is going to tell us whether it's concave up or concave down. So deriving it again, we get negative 12x plus 12. At x equals 3, we're going to sub that in. So negative 12 times 3 is negative 36, plus 12 is negative 24. This tells us that the graph is concave down at that point. B is to work out the coordinates of the point of inflection. That is to let the second derivative equal 0 and solve for x. So solution is 1. If we test either side, we can go and sub in x equals 0 or x equals 2. That's going left 1 and right 1. Now if we sub 0 into here, or we sub 2 into here, that tells us the second derivative at those 2 points. The first one is 12. The second one is negative 12. Hence the concavity changes. Therefore, it's an oblique point of inflection at 1, 4, or x equals 1, y equals 4. Just have a quick look at the graph here. At 3, that graph there is concave down. At x equals 1, which is here, that's an oblique point of inflection where a concave up meets a concave down. Determine the second derivative of the following functions. Here we have a trig function, 4 sine 3x. Using the chain rule, the derivative of 3x is 3. We keep the 4. Sine changes to cos, and the function stays the same. The angle, 3x. So we have 12 cos 3x. To work out the second derivative, we'll apply the same method. 3 times 12, cos changes to negative sine, and the angle 3x stays the same. So the second derivative is negative 36 sine of 3x. In the second one, we have a natural base e exponential function. The derivative of 4x take 1 is 4, so that comes to the front, and our power stays the same. If we did it again, 4 times 4 is going to be 16, e to the 4x take 1. It's a nice short one. Question 5. The number of organisms at any time t is given by nt equals 20t e to the negative 0.2t. Calculate the maximum population. I've first of all graphed it, which you don't necessarily have to do, but if it's a tech active question, we could solve by graphing. I'm going to use algebraic techniques to determine the maximum population, which looks like it happens at about 5. Now, because this is a function times a function, if you let that equal u and e to the negative 0.2t equal v, you could then find u dash and v dash, and your product rule is u v dash plus vu dash, which I have here. Now I'm going to simplify this. 20 multiplied by negative 0.2 would be negative 4. Now I'm going to keep that 20 there. And next step is to factorize. Negative 4e to the negative 0.2t is common. That's our highest common factor. And then I'm left with a t take 5. To work out a maximum, I'm going to let my first derivative equal 0. And that's a function times a function, so I can apply the null factor law and let this equal 0 and let this equal 0. This equaling 0 is not going to work, so I'm left with t take 5 equals 0. Hence my answer is t equals 5. The maximum population is when I sub in a 5 to this original function, which is 20 times 5 e to the negative 0.2 times 5. So maximum population occurs at t equals 5, which is 36.8, or whatever this organism is, which matches up with this graph. Particle moves in a straight line. Its position, x, with relation to t, is given by the following cubic, where units are meters and seconds. Calculate an equation for velocity at any time. Velocity is the derivative of position. To differentiate, define velocity. If we differentiate that, that's just using your plain old simple polynomial power rule for differentiation. So 3 times negative 2 is negative 6, divided by 3 is negative 2. 8 times 2 is 16, take 1 off the power, and 5 disappears. So we have dx dt, which is velocity. Calculate the maximum velocity of the particle and the time and location that this occurs. So to work out maximum velocity, you want to maximize this equation here. To do that, you differentiate and let the derivative equal 0. So my second derivative, or acceleration, is 2 times negative 2 is negative 4t plus 16. Let that equal 0. Rearrange by subtracting 16 from both sides. Divide both sides by negative 4. The time is 4 seconds. Velocity at that time is to sub the 4 back into your velocity equation, and by doing so, I find that it's 32 meters per second. The location is to sub 4 back into the original position function, and if I do that, the object was at a position in a straight line of 218 1/3 meters. You could have changed dx dt and written it as vt, v bracket t, and same with the second derivative, that could be expressed as acceleration, so you could write a bracket t. Determine the second derivative if y equals 3 the natural log of x squared plus 1. Use the chain rule to differentiate. So y equals 3 ln u, where u is x squared plus 1. So dy du is 3 lots of 1 on u, that's the derivative of ln u. Du dx is nice, it's just 2x. So the chain rule formally now is dy dx equals dy du multiplied by du dx. Substitute both of these in. So 3 over u times 2 to the x is 3 times 2x is 6x, and replace the u with your x squared plus 1. That's the first derivative. Now we have to work out the second derivative, and to do that, you need to use the quotient rule because you've got a function divided by a function. So u is 6x, v is x squared plus 1. The derivative of u is 6, so du dx is 6, dv dx is 2x. The quotient rule, vu dash take uv dash over v squared. You've got your 1, 2, 3, 4 expressions here. Sub those all in. So your v was your x squared plus 1, your du dx was 6, and so on. And your job is to simplify. So what I've done here is 6 times x squared is 6x squared. 6 multiplied by 1 is 6. Negative 6x multiplied by 2x is negative 12x squared. Those two are like terms. So I have a numerator that's now 6. Take 6x squared all over x squared plus 1 to the power of 2. That's our second derivative. I'm going to use the chain rule and the quotient rule. Consider the function fx equals x cubed plus 9x squared plus 15x plus 2, where x is any real number. Determine the coordinates of the stationary points and use the second derivative to describe their nature. First of all, using the power rule, the derivative is 3x squared plus 18x plus 15. Now, a stationary point is going to be when f dash equals 0. So let's let that equal 0. We have a quadratic. I'm going to factorize out the 3. Now I can simply factorize x squared plus 6x plus 5, which is x plus 1 multiplied by x plus 5. Null factor law, my solutions are negative 1 and negative 5. That's the stationary points. And where they occur is me subbing those two values in to the original function. At negative 1, my y value is negative 5. At negative 5 across, the y value is 27. Now the second derivative. The second derivative is deriving the first, which is 6x plus 18. Now what I'm doing now is subbing in negative 1, one of our stationary points, into the second derivative, and it equals 12, which means it's telling you that it's a maximum min. At the coordinate location x equals negative 1 and y equals negative 5, the second derivative showed us it was positive, hence the point is a local min. Do the same now for x equals negative 5. The second derivative is a negative value. The negative value tells us that at that point it's a local max. The second derivative will equal 0 at points of inflection. So second derivative, letting equal 0, we subtract 18 from both sides, then divide by 6, x equals negative 3. If we sub in negative 3 to our original function, the y value is 11. Now that point of inflection is going to be an oblique point of inflection because negative 3 wasn't picked up in the first derivative. Hence, it's not a horizontal point of inflection. Therefore, the point of inflection oblique occurs at negative 3, 11. Consider the function fx equals 4x times e to the x, where x is less than or equal to 2. Determine the coordinates of the stationary points and use the second derivative to describe their nature. First of all, we're going to have to use the product rule, where 4x is u and e to the x is v. So u is going to be your 4x, the derivative of e to the x is e to the x, the derivative of 4x is 4, and v is e to the x. If I factorize out the 4e to the x, which is common to both terms, I'm left with 4e to the x outside of x plus 1. The second derivative would be the same, where this is u and this is v. So u is your 4e to the x, your v dash is the derivative of x, which is 1, so I'm left with 4e to the x. Then you're going to have your u dash, which is 4e to the x, times v, which is x plus 1. Factorizing again, 4e to the x outside of 1 plus x plus 1, which is 4e to the x outside of x plus 2. Now, we're going to determine stationary points by letting the first derivative equal 0. The null factor law, 4e to the x equals 0, and x plus 1 equals 0. You're not going to get a solution for this one. There's a horizontal asymptote at y equals 0, but here our solution is negative 1. Now I've subbed in negative 1 to the original function, and the y value is negative 1.47. The nature is subbing in negative 1 to the second derivative, which I've done so here. I've subbed in negative 1. Now 2 plus negative 1 is 1, and I'm going to write this as 4 over e because writing that for the positive indice. Now 4 over e is a positive number, therefore it's a local min. The points of inflection is letting the second derivative equals 0. Null factor law, 4e to the x equals 0, and x plus 2 equals 0. We're not going to get a solution for that one, but for this one, our solution is x equals negative 2. There's a point of inflection at negative 2 across, and our y value after subbing it in is negative 1.08. I'm going to graph this. Here was that local minimum, which is actually a global minimum, and a point of inflection was here. The graphing there is just an extra bit for you to see how it turns out. Question 10 is an application question. Postal cylinders are made according to the rule that the sum of the length and circumference should be less than 150 centimeters. Calculate the dimensions of the cylinder with a maximum volume. So our length plus our circumference should be less than 150. So we'll evaluate this for being 150. I can rearrange that, make an expression for L, which is 150 take 2 pi r. That's equation 1. Equation 2 was that the volume of a cylinder is the area base times height, so it's pi r squared times height. That's the thing we've got to maximize. So that's equation 2. Now the height of a cylinder is its length. So what I've done is subbed in the length here for h, which is 150 take 2 pi r. Now if we expand this, we get 150 pi r squared take 2 pi squared r cubed. Just think of pi squared as a constant, so it's 2 pi squared is the coefficient. You now have the function, so you can just differentiate by using the power rule. So 2 times 150, 3 times negative 2, take 1 off the power in both cases, and you have your derivative, your first derivative. That's the hardest bit because you've got to this point, you now let the derivative equal 0, and you solve. So here, I can see that a pi is common and an r is common to both of those, and a 6. So 6 pi r is the highest common factor outside of 50 take pi r. Null factor law, 6 pi r equals 0, or 50 take pi r equals 0. Now if we evaluate that second factor, you're then going to have a solution where pi r equals 50, which means r is 50 divided by pi, which is approximately 15.9. Now that you've got r, you can sub it in over here to work out L. So L is 50. So the dimensions are the length or height has to be 50. The radius has to be about 15.9154. So the cylinder with the largest volume has a length of 50 centimeters and a diameter of about 31.8, or a radius of 15.914 centimeters. And that concludes our session on applications of derivatives. Keep working on your studies and good luck in your exams as usual.